these are some more examples for comparison tests. And what we're going to be using is those two little rules that we had before. So if you have r to the n, as long as r is less than 1, we have convergent. And if we have 1 over n to the p, as long as p is greater than 1, we're going to get convergence. So these are the b sub n's that we're looking for. And obviously, if r is greater than 1, it's going to diverge. And if p is less than or equal to 1, it's going to diverge as well. So if you look at this, our a sub n here, right, is going to be that 6n over 5n minus 1. And so for picking your b sub n, what you want to do is just eliminate everything without that n, or stuff that's not that big that we can use for our additions and subtractions and remove it. So we're looking for those general leading terms. That's what we want to find. Because then you can take your b sub n and rewrite it like this, and we can go back up and apply our ratio test. So you can see here that that 6/5 is going to be bigger than 1, meaning this is divergent. So since we know it's going to be divergent, we go to our divergent. We want it to be greater than. And so we're going to say our a sub n, which is 6 to the n 5n minus 1, is greater than 6 to the n over 5n, which equals 6 over 5 to the n. And so then we know that the sum from n equals 1 to infinity of 6 over 5 to the n is divergent because our r is greater than 1 in this situation. And you can put the equal on there if you want. But because that's divergent, so by the comparison test, the sum from n equals 1 to infinity of 6n over 5n minus 1 is also divergent. Because we found out that the smaller one is divergent, so the bigger one also has to be divergent. So that's the basic idea if you want to apply the comparison test. You find some b sub n that you know will comply to what we're looking for, which is convergent or divergent, and go from there. So what do you do when you have a sine? Well, sine we know is not going to go bigger than 1. So we know our a sub n here is n sine squared n over 1 plus n cubed. So our b sub n, where we want to start it with, is just the n over n cubed. You can see them here. We have an adding 1 and a 1. And so this would be 1 over n squared, which we know is convergent. So we go back up, and we now need to be able to make sure that we apply our rules correctly so that we have less than, because that's convergent. So our a sub n, which is n sine squared n over 1 plus n cubed, is less than, right? And I'm going to get rid of just that sign. So 1 plus n cubed, just so that we have it. And then we make sure that we can do that bottom. So again, if you're adding something to the bottom of the fraction, that would make that fraction smaller. So that means this is less than n over n cubed, which is n over n squared. Oops, it's not, it's 1. And so we know the sum from n equals 1 to infinity of 1 over n squared is convergent because our p is greater than 1. That's what we're looking for up there, right? P greater than 1. All right, so if that's convergent, then by the comparison test, well, that looks horrible. Let me try that again. By the comparison test, the sum from n equals 1 to infinity of n sine squared n over 1 plus n cubed is convergent. All right, let's try another one. So here the same idea. And so you see cosine n, it's not going to get bigger than 1. And so 1 plus 1 would be 2. And we have 2 over e to the n, right? And so if you look at the e to the n, we would say that our a sub n here is 1 plus cosine n, not con n, cosine n, and we have e to the n. And so our b sub n is most likely going to be 2 over e to the n. Now, if you have e to the n, you're thinking, okay, well, what is that? Well, this is just 2, right? And then it's 1 over e to the n. So if you have an n for the exponent, that means we're talking about ratios. And so it's that whole idea as long as our r is less than 1, our series is going to converge. And that's what we have here. 1 over e is less than 1. So we know this is going to be a converging one. So converging means less than. So a sub n equals 1 plus cosine n over e to the n, which is less than, and that's 2 over e to the n. Now it could be equal to, so I'm going to put that on there. So cosine n can't go bigger than 1, right? So 1 plus 1 would be 2. So this has to be less than 2 over e to the n, 100%. All right, so then this would be 2, 1 e to the power of n. And so we know that the sum, and I'm going to put the 2 outside, of n equals 1 to infinity of 1 over e to the n is convergent. Because again, our r is less than 1. So by the comparison test, the sum from n equals 1 to infinity of 1 plus cosine n over e to the n is convergent. So as long as you're showing that your a sub n is less than something that converges, it's convergent. And if you're showing your a sub n is bigger than something that is divergent, sorry. So a sub n is bigger than something that is divergent, then that, by comparison theory, it will be divergent. And there you go. Let me zoom out a little bit more.